Assalamualaikum and good day everybody. It is a pleasure to be here at the Colloquium Penyelidikan 2022. My name is Syahrim Azhan bin Ibrahim from Malaysia Space Agency or MISA. I will be presenting a part of my PhD study which is entitled Solar Radiation Disturbance on Deployable Solar Panels of Nano Satellite. The study was done in Kyushu Institute of Technology or QTech under supervision of Professor Eki Yamaguchi. The outline of my presentation is as shown in this slide. Firstly, I will introduce you to Nano Satellite. As is known, an artificial satellite is an object that is intentionally placed into an orbit or circle around a larger object. Nano Satellite is a type of artificial satellite that is relatively small in size with mass between 1 to 10 kg. And it usually follows a specification called CubeSats. As you can expect, a CubeSat is shaped like a cube, about 10 cm wide, long and deep. That is called a unit or 1U. Like building blocks, units can be combined to make bigger CubeSats by stacking them so you can have 1.5U, 2U, 3U, or even 6 units. With the bigger size, we can place more parts for more complex missions, which may require solar panels that can be deployed to generate more power for the CubeSat system. CubeSats are great because they are made from standard, low-cost, readily available parts that allow universities and other teams to launch their very own missions in outer space. In Malaysia, the CubeSat standard has been adopted and successfully launched by a private firm, ATSB, and a university, UiTM, both in 2018. Currently, most nanosatellites are deployed in low Earth orbit, or LEO, which have altitudes ranging between 250 km to 2000 km from the Earth's surface. In LEO, the main external disturbances for satellites are gravitational gradients, magnetic fields, aerodynamic drag, and also solar radiation. As shown in figure 3, the amount of solar radiation is almost constant around the Earth. However, the force exerted on each individual satellite depends on the surface area facing solar radiation. Recently, since there are more CubeSats use deployable solar arrays or solar panels to increase solar power generation, there is a need to make a study about the characteristic of solar radiation on those nanosatellites. As shown in figure 4, satellites in low Earth orbit will experience periodic heating in sunlight and cooling in shadow regions of the Earth. Referring to figure 5, the transition from shadow region or eclipse to daylight is especially critical, as the satellite will experience sudden thermal loading, which can generate an impulsive torque on the deployable solar panel, resulting in dynamic response, also known as thermally induced dynamics, or TID. The TID phenomena on the solar panel has been known to affect the orientation of LEO satellites during eclipse transition. As shown in this figure, the sudden thermal loading from solar radiation can force the solar panel to move downward from its original position, resulting in orientation of the satellite body in the opposite direction due to inertia effect. Majority of CubeSats are low Earth orbiting. From the literature review made, available research focus on large satellites whose size and mass are in orders of magnitude larger than miniaturized satellite like CubeSat. Since large satellites normally have one or two more large solar panels, the effect of TID disturbance on the orientation, or we can also call it as attitude dynamics of the satellites, mostly were studied analytically using a simple spacecraft consisting of a rigid body and one or two beams to represent the solar panels. CubeSats, on the other hand, could even have 4 panels. Therefore, there is an apparent lack of studies on how this phenomenon could affect the CubeSat attitude dynamics, although the usage of deployable solar panels has become more popular in recent times. Moreover, in anticipation of future advanced mission requirements, prior investigation regarding TID is worthwhile so that necessary countermeasures can be implemented if required. Given this apparent research gap, the following question is addressed in this research. How can the attitude dynamics of a CubeSat mounted with deployable solar panels be affected by TID phenomena? The methodology used in this research has four major procedures, beginning with determining the analysis model and thermal environments to set the scope of the research. Some of the info is shown here in figure 7. From there, we run thermal analysis using a software called Thermal Desktop to obtain temperature profiles of our model. Then, based on the temperature data we had, we ran thermal structural analysis in Abacus, a finite element software to classify the types of TID disturbances that could occur. Finally, we ran attitude dynamics analysis using the inertial relief method in Abacus software to quantify the satellite's rotation due to the TID effect. In this slide, I will show some of the important results obtained from each analysis done in the procedures. Thermal analysis is the first part of the analysis. Its purpose is to obtain the temperature average on different layers of the deployable solar panels during the shadow to sunlight transition as a function of orbit time. In brief, from the thermal space environment settings in the orbit of interest, we can obtain the total external heat absorbed by the top and bottom surfaces of the deployable solar panels. Figure 8 shows the absorbed heat in one orbit period. From there, we can obtain the temperature of each layer of the solar panels, as shown in figure 9. The second part of analysis is called thermal structural analysis. The function is to classify the types of TID disturbances that may occur on the current CubeSat model and quantify their levels. On the finding of this analysis, as expected, due to the change of heat absorbed along the orbit trajectory, the temperature of the solar panel varies accordingly. In the shadow region, the entire solar panel structure is almost at the same temperature, and then changes occur when they enter the sunlight, as their temperature will increase differently depending on the position of layers and material properties. The temperature results that we obtain are then used in the thermal structural analysis, which is used to classify the types of TID disturbances that may occur on the current CubeSat model and quantify their levels. As obtained in the thermal analysis, whenever the satellite is in the sunlight region, the upper side of the solar panel will get hotter than the bottom part. This causes the solar panel to deform downward or bending, which is one type of TID phenomenon we name as quasi-static deformation. However, right during the transition from shadow to sunlight or vice versa, sudden decline and incline in displacement occur due to the rapid increase and decrease in temperature differences across the cross-section of the solar panel. For example, due to the sudden displacement when the satellite is in transition from shadow to sunlight region, the solar panel will experience velocity and acceleration transients that will impose a dynamic response from the solar panel. This type of dynamic response can be characterized as another TID phenomena called thermal snap. The final analysis is the pointing displacement analysis that is used to quantify the change in the orientation of the satellite body due to disturbance torque produced by the acceleration motion of the solar panels. In order to do that, we choose one point of the body as a reference and use the inertial relief method or IRM to find the displacement of one point on the satellite body to check the rotation. The displacement are defined as rotation around the X, Y and Z axis, and all of them can be obtained through the inertial relief method. Figure 13 depicts the undeformed and deformed states of the CubeSats after inertial relief analysis. The procedure is further tested on 4 CubeSat models with various deployable solar panels configuration as presented in figure 14. From there, the study made several other observations and conclusions on the level of the satellite orientation due to the TID phenomena. In this research, some simplification is made to the CubeSat structure and some parameters in the space environment. For example, the material properties are assumed not degraded from exposure to the harsh space environment. However, since a nanosatellite normally has a short average operational lifetime, that assumption can be considered acceptable. Secondly, this work only examines an LEO mission where the solar cells of the solar panels point to the sun throughout the daylight period and point to the earth while in shadow. However, in selecting this mission, we consider that the mission would be the worst case scenario for the TID phenomena could affect the current CubeSat model that we use. In terms of the importance of the study, the result from this work reveals several practical applications worthy of simplifying the study of TID on nanosatellites deployable solar panels. Most importantly, the study presents complete analysis from thermal to structural and concludes with pointing displacement analysis in a 3D model using finite element software. As far as nanosatellite technology is concerned in Malaysia, much remains to be done to enable small satellite technology to be used by government, academia and private sector in their work. However, in my opinion, the launch of UITM-SAT has certainly improved motivation and enthusiasm in the technology. This can be seen in terms of growing interest from private firms and local universities to conduct tests at MISA's Assembly Integration and Test or AIT facility for satellite in Banting, Selangor. Inside MISA, our management is trying to facilitate this, for example by encouraging MISA staff to improve their knowledge in the subject matters whenever there is an opportunity. For example, through a program between JPA and Japan International Collaboration Agency, MISA sent 9 researchers to QTech's Center of Nanosatellite Testing to learn about the design and testing of nanosatellites. When it comes to relevant government policies, this effort is part of the strategic thrust contained in the National Science, Technology and Innovation Policy that is to advance scientific research in government agencies, as well as Thrust 3 in the National Space Policy 2030 that is to drive the development of space science, technology and increase expertise. In the latter policy, to implement the thrust, first is to coordinate priorities and activities of research, development, commercialization and innovation as well as training in space technology. Some activities that will be done and also ongoing is CANSAT competition for universities and school students, as well as collaboration with local industry and university to build a CubeSat through researcher industry scientific exchange program. Second implementation is to develop local expertise and competitive domestic industry capabilities. In doing so, MISA is now trying to further accommodate our testing facilities for nanosatellites through the use of our existing equipment and upgrades. To conclude this presentation, a computational method that combines usage of a thermal analysis software and finite element analysis software to investigate TID phenomenon on a satellite in LEO has been presented. Last but not least, personally, I believe that the skills and experience gained by MISA's researchers at QTech can assist MISA in contributing to government policy to increase R&D activities in the space sector. With that, I finish my presentation. Thank you very much.